Mr. Antonucci here, and in this video, we're going to talk about Rolle's theorem and run through a couple examples. Here's how it works. Suppose f is a function on a closed interval a to b. So graphically, here's a, here's b, and those are the endpoints right there. Now, there are three conditions for Rolle's theorem to apply. One, if f is continuous on the closed interval a to b. Two, if f is differentiable in between, and if the endpoints equal one another, f of a equals f of b. Then there is at least one number, we'll call it c, in the open interval a to b, so in between the endpoints, for which f prime of c equals 0. So if you look at the graph here, we have f of a equals f of b, and at least one point in between, namely here, and there's also another one here, the slope of the tangent line is equal to 0. So notice this is an if-then type statement. If the function is continuous on a closed interval, if the function is differentiable in between the endpoints of that interval, and if the endpoints have the same y value, then we know at least one number in between the endpoints, the derivative is going to be equal to 0. Here's a couple examples that don't work. This first one, the function is defined on the interval from a to b. It's a closed interval, but it's not continuous at the left endpoint. Also, this function is differentiable in between the endpoints. The function is smooth and continuous between a and b. And f of a does not equal f of b. So even though there is a point where the derivative equals 0, Rolle's theorem does not apply because it breaks one of the three conditions. This second graph, notice the function is continuous between a and b, and f of a equals f of b. The y values are the same. But notice there is a point where f prime does not exist in between the endpoints. In other words, this function is not differentiable on the entire interval between a and b, so Rolle's theorem does not apply. And finally, this third example, here's a and b. The function is continuous on the interval a to b. It's differentiable on the interval a to b, but f of a does not equal f of b, so Rolle's theorem does not apply. So if you're trying to use Rolle's theorem, it is very, very important that you show that the function you're working with satisfies the conditions before you try to talk about the conclusion. So here's an example. We want to verify that Rolle's theorem applies to the function x cubed minus 6x squared on the closed interval 0 to 6. Then find all values of c in that interval 0 to 6 guaranteed by Rolle's theorem. So the first thing we want to note is the function continuous. Well, it is continuous because it's a polynomial, and all polynomials are continuous on their domain. Second, it is differentiable on the interval 0 to 6, again, because the function is a polynomial, and polynomials are differentiable on their domains. And then third, f of 0 does equal f of 6. Those both equal 0. So the function is continuous on the closed interval 0 to 6. It's differentiable on the open interval 0 to 6, and the endpoints have the same y value. Therefore, we know that f prime of c equals 0 for some value c between 0 and 6. So to find that, we would just take the derivative and set it equal to 0. We could factor out a 3x, and we get x equals 0 and x equals 4. Now, an important point here is that the c value guaranteed by Rolle's theorem is only 4, not also 0, because remember, the conclusion of Rolle's theorem is that the c value is on the open interval, in this case 0 to 6, so it's in between the endpoints. So even though we got two values, you only report the values that exist on the interval. So here we have the graph of the function. In the braces here from 0 to 6, I just restricted the domain from 0 to 6. If I do f of 0, you get 0. If we do f of 6, we get 0. and then we can determine that the derivative is going to equal 0 for some value in between 0 and 6. We could easily graph the derivative just by plugging in f prime. And notice that this point right here, the purple graph, which is the derivative, is equal to 0 when x is 4. It's also equal to 0 when x is 0, but we don't include that one because, again, it's not in between the endpoints of our desired interval. So we knew this was going to happen because Rolle's theorem applies to the original function. And here we just verified graphically that it occurs at the point when x is 4. So here's another example. We want to find the x-intercepts of x squared minus 5x plus 6 and show that f prime of c equals 0 for some number c in the open interval formed by the two x-intercepts. Then we want to find the value of c. So the x-intercepts are when x squared minus 5x plus 6 equals 0. We can factor this to x minus 2 times x minus 3. And we would get x equals 2 and x equals 3. So we know that f of 2 equals f of 3, which equals 0, and those are the x-intercepts. Now, if we want to show that f prime of c equals 0, this is asking us, without stating it, to use Rolle's theorem. So we want to show that 1, f is continuous on the closed interval 2 to 3. That's between the intercepts. And that's true because f is a polynomial. And 2, f is differentiable on the open interval 2 to 3. Again, because f is a polynomial. And 3, we already showed that f of 2 equals f of 3 equals 0. In other words, the endpoints have the same y value. You have to explicitly show that these three conditions are satisfied, like I just did here, in order to apply Rolle's theorem. Therefore, Rolle's theorem applies. So we take the derivative, set it equal to 0, and solve for x. So add 5, divide by 2, that's equal to 2.5. 2.5 is in between the endpoints of x equals 2 and x equals 3. So that is the c value guaranteed by Rolle's theorem. Just to show you graphically what's going on here, here is the graph of the function. We have the x-intercepts right here, which we can export very easily to our menu. And then we could verify that f of 2 equals 0 and f of 3 equals 0. Then if we graph the derivative, we can see that the derivative's graph is equal to 0 at some point, at least one time, in between the interval 2 and 3. Notice also this point graphically is where the original function changes direction, what we would call the local minimum. All right, guys, that's it for Rolle's theorem. Hope that was helpful to you. Make sure you give this video a like and subscribe to the channel because I will be releasing more videos for calculus.